I have a lot of material, and I'm not sure I'm going to be able to cover it all, but this is the plan, and it's modularized, so I will omit something if I run out of time. So the problems I'm going to talk about involve an interaction between physics and mathematics, starting with crystals. So I'll do crystals, then I'll discuss quasicrystals, then I will discuss discrete geometry, problems related to that, a taxonomy for Delaunay sets, and characterizing ideal crystals. And then I will explain in the middle, the connection, a viewpoint that's proved very fruitful, which is the use of dynamical systems and harmonic analysis in some of this study. So let me begin with crystals. So the word crystal is a Greek word meaning ice. It was used originally to describe quartz crystals, and then afterwards was generalized to crystals of all sorts, meaning materials that have the beautiful appearance, as exemplified in the collection of Steve Smale. And in the 19th century, models were made to try to explain the structure of crystals, and this subject is sometimes called geometric crystallography. It started in the mid-19th century, and it predated the proof that materials are made of atoms, which only occurred in the early 20th century. But the models were atomic, and so our model will represent some infinite material with a symmetry. So we'll be concerned with infinite discrete set of points in n-dimensional Euclidean space. And these are the 2 and 3 dimensions were what were studied. And I will use a term, Delaunay set, named after the Russian mathematician B.N. Delaunay. His name is spelled either of those 2 ways, depending on which subject you're in. You probably see both. He preferred this spelling. And those are sets which have points distributed through space densely, so they're not too close and not too far apart. So there's some radius little r such that no 2 points are within distance little r of each other, and there's some distance big R which is bigger, such that every ball of that radius contains at least 1 point. So those 2 properties are relative density. There's a finite covering radius for spheres at those points, and uniformly discrete, there's a finite packing radius for spheres of those points. So you can think of this as a model for solid state materials with the points representing atomic positions. So here is the definition of a crystal I'm going to use in mathematical crystal. It will be a finite number of translates of a full dimensional lattice. So a lattice is a discrete additive subgroup generated, in this case, an Rn by n linearly independent vectors, say Z2 in the plane, and then we allow a finite number of shifts of those, and the concept in geometric crystallography that was originally proposed was to give a very symmetrical system of points. So a regular point system, defined in the mid-19th century, will be a set of points with the property that, first of all, they form a Delaunay set, and second of all, they look the same from every point. That means if you shift the mass, so a particular point is at the origin, there's an isometry of space that will map the configuration onto itself and will act transitively on the points. So if you're a bug centered at any point of the object, it looks the same every place. All you can see is where the other points are away from you, and they're identical up to an isometry. So the symmetry I will attach to that is a crystallographic group. This is not the modern definition. The original definition was it would be a symmetry group of some regular point system, that is, the set of isometries of space that will map the regular point system onto itself. And the basic problem there is to classify crystallographic groups. And this was done in the 1870s, maybe not quite to current mathematical standards, that there are 17 two-dimensional crystallographic groups. And of course, the case of interest was 3 dimensions because we wanted to describe all the structures of crystals, and that was done separately by, I guess, 3 physicists, in the early 1890s that there are 230 three-dimensional crystallographic groups the way they are classified here. None of them got an exactly complete list. Each of them missed at least one. Some of them had duplicates, but between them they got them all. And this may make you wonder about the reliability of mathematical proofs, which will. The definition now mathematically is as a finite discrete group of Euclidean motions, which when you quotient out the Euclidean motion group by that discrete subgroup, you get a compact manifold, co-compact group. And then we classify them up to isometry, and then the count becomes slightly different. So there are 54 proper ones where determinant -1 is not allowed, and then 219. You get a slightly different count than the physicists. Now, why do I bring this up? Because this classification came from crystallography, but Hilbert liked it, and one of his problems is based on questions coming from crystallography, and that is his 18th problem. So of his 23 problems, or 24 if you count one unofficial one, number 18 had 3 parts. So the first part is, in n-dimensional Euclidean space, is it true that there are finitely many essentially different groups of motions with a fundamental region? So at that point, the 2- and 3-dimensional cases had been solved, and there was a finite list. And he asked, was this true in n dimensions? And the second thing is, of course, when you quotient out by the group, you can find a fundamental domain. And in all the cases known, this could be done with a polyhedron. And his second question was whether polyhedra exist which could be used to tile space, but which are not a fundamental domain for some compact group of motions acting on space. And then there was a third part. And the third part was, what is the most dense packing of spheres in 3-dimensional space, the Kepler problem, and what is the most dense packing of regular tetrahedra in 3-dimensional space? And the status of these problems is the following. The first part was solved by Bieberbach in 1910 and 1912 when he proceeded to classify discrete co-compact subgroups of the n-dimensional Euclidean group of motions. The second problem was solved somewhat later. The first example in 3 dimensions was found by Reinhardt of a fundamental domain that does not that tiles but doesn't come a non-convex polyhedron that does not tile, that does tile space, and is not a fundamental domain of a group of motions. And then Heesch came up with a non-convex 2-dimensional example. And then in the early 90s, Schmidt found a construction that was refined by Conway and Dancer that produced a beautiful example in 3-dimensional space. So this, in the Heesch example, in 2 dimensions of tile space, it's not a fundamental domain, but if you put 2 copies together by with one rotated to fit in the other, then you do get a fundamental domain. So the thing gave you a miss by something of index 2. But the Conway-Dancer example in 3 dimensions, which is a perfectly nice convex polyhedron with 8 faces consisting of 2 prisms glued together, properly arranged, has the property that it tiles space, but every tiling is aperiodic. And that this comes about because you can tile in 2-dimensional layers, and then there's a screw motion built in with an irrational rotation. And one has to do some work to prove that that you've got absolutely all the tilings that way, and every one is aperiodic. Now, I would like to say a little more about go back to the Bieberbach case because it is relevant to the quasi-crystal situation. So Bieberbach's first result, which is the key result about analyzing the Euclidean group, is that any discrete group of isometries with a compact fundamental domain has to contain inside it a full rank lattice of translations. And that lattice by itself already gives you co-compactness. And then this full rank lattice is then a finite index in the whole group. And in fact, it's a normal, I believe it's a normal subgroup. And so the conclusion one gets from this is that because of the existence of this lattice, there are only a finite number of cosets because it's a finite index. So you get the result that every regular point system is necessarily a periodic crystal, as I've defined it, an ideal crystal, finite number of translates of a lattice. However, it is not true that every finite set of translates of a lattice actually looks the same at every point. It might actually look in finite number of different ways depending on which point you are in the fundamental domain of in the unit cell of the lattice itself. The second thing is this finite index is can be associated to a subgroup of the orthogonal group. And one gets from this the action of that orthogonal group on the lattice has to preserve the lattice. And so we get the so-called crystallographic restriction, which says any Euclidean motion that fixes a point of the object necessarily leaves the lattice invariant. And that means that the finite index, the intersection with you have to quotient out to get the piece of the orthogonal group, that point group must be conjugate to a finite subgroup of GLNZ. And that the finite groups of GLN are bounded by another one of Bieberbach's theorems. And so in every dimension, there's some upper bound on how big the point group can be. And in dimension 3, since everything in it is a finite order, you can prove the only orders you're allowed to get are 1, 2, 3, 4, and 6 for crystals in R3. So that brings me to quasicrystals. So in 1982, Danny Scheckman, who was the National Bureau of Standards, was in the midst of doing some other experiments, but they were preparing materials by rapid melting, by heating them up high and then very rapidly cooling them down. And in this way, he made a material which is a mixture of aluminum and manganese, whose electron diffraction image indicated that the atoms in it had long-range order because the diffraction patterns had a series of discrete spots. In fact, this had been observed soon after the invention of X-rays, that when they were run through crystals, the observation that you get diffraction patterns consisting of discrete spots indicated some kind of order in the material. But the indicated order had icosahedral symmetry. And in particular, it had some symmetries of order 10. And 10 is impossible for a crystal because it violates the crystallographic restriction. And as a consequence, he was unable to get any paper on this published in physics literature. And so what he did was, since he was in Maryland, he went over to Johns Hopkins, where he found one of the premier experts in material science named Kahn, and he managed to convince him that these experiments were for real, and they published a joint paper 2 years later. Science is the peer review process in science is much tougher in some ways. It's more tough in some ways, and it's less tough in other ways. So you don't have to have a proof, but you have to convince the reviewers. All right, so they published this paper. It made a furore. It was a very exciting time in physics, and many people came out and said this was absolutely not for real. So, for example, Linus Pauling argued that this phenomenon of the five-fold symmetry was due to twinning in the crystals, and many people objected. So then what happened was people succeeded in growing quasicrystals to macroscopic sizes. So here is one that's about 1/10 of an inch across. At Bell Labs, for example, they were able to grow quasicrystals that appear when grown, they appear to be similar to crystals in their appearance. And this one was a regular dodecahedron, which according to the crystal theory is an impossible shape for the wolf shape of a crystal. At Bell Labs, they've grown them to be 1 inch across. The argument continued, and eventually they succeeded in growing some of them. This particular material, aluminum, aluminum, copper, iron is the nicest one. They grew big ones, and then they were able to take electron microscope photographs of where the atoms are. And they were able to observe some kinds of five-fold symmetry on the atomic level. So it's been drawn in here. But even if you look locally, you would be able to see many, many clusters. So this is 20 angstroms across there. Now, there is one cheat in these photos, which are that it's photographing in one direction, so you're seeing columns of atoms rather than individual atoms in this photo. But the current state of quasicrystals is that I think there are about 200 different reasonable quasicrystalline materials that are known. There are some that are thermodynamically stable, apparently, and in some ways can be grown to large sizes and appear to be as perfect as crystals, and they look like crystals when they're grown to large size. You get a polyhedral wolf shape for the object. And then there are a lot more of them that are believed to have some degree of disorder at the atomic level that's positive entropy, and they are presumably stabilized only at certain combinations of temperature and pressure. But the ones I'm interested in here would be the perfect ones. So that goes to the motivating problem. So now we can come to some of the motivating problems for quasicrystals. By the way, these materials are now used commercially. They're used in non-stick bearings. They have managed to make, somebody sells a fry pan whose base is a non-stick fry pan whose base is essentially a solid quasicrystal film. It's like Teflon, but you can't scratch it. I mean, they actually did experiment. So it's some very high-end thing for cooks who only want the best. So they did experiments with a spatula on this thing, and they used to rub the spatula across that, and they noticed there were metallic flakes, and they said, look, the coating has come off, but no, the coating was so hard it actually ripped off the end of the spatula. All right, well, but we aren't concerned with that here. So here are some mathematical questions. The first thing is to explain why is it that the electron micrographs allow pure point diffraction, which certifies you have a crystal, but it has extra symmetries that are not permitted. So one needs a mathematical model for diffraction there. And the second question is, where are the atoms in these objects? Because they cannot have a full rank lattice of symmetries in them. So the ordering of the atoms has to be aperiodic in some sense. It can't be fully periodic. In fact, the examples show that it could be completely aperiodic. And there are answers to this, some coming from discrete geometry models, and then there's a strong connection with dynamical systems that I will explain. And then there is another question, which is how could these materials form, given that the order is aperiodic, but there is some kind of long-range order in the atoms, so how do they know where to go? And here one can give a kind of answer involving local rules, which are locally energy-minimizing arrangements of atoms. I should say, by the way, that the mathematical physics has not succeeded in proving the existence of crystals, so one can't really hope to, that is to say, they haven't managed to find a reasonable functional of which the ground state energy would correspond to a material wanting to form itself into a crystal with the lattice structure. That's not known, so you can't hope for such an answer there. And then finally, the existence of these objects leads to a question which didn't come up before, but what is the boundary? How much regularity do you have to force on a geometric object to force it to be a crystal, as opposed to being a quasi-crystalline object which will have a lot of symmetry but not enough to enforce the underlying lattice structure? So before going into details, let me just mention that the subject has developed very nicely now, and the mathematics that it's been used involves the following ingredients. Well, it involves group theory to try to classify, given that more symmetries than were thought to occur before have occurred, can you classify all the extra symmetries you might get for these materials? And in fact, you can get some very strange symmetry groups. The second thing is that when you try to look at these things to explain diffraction, then both of the diffraction and the symmetries lead to questions in harmonic analysis involving representations of groups, where the group here would be the group of Euclidean motions. Then finally, there's the discrete geometry aspect, which is where the atoms. Let's look at Delaunay sets and ask what kind of properties must these sets satisfy to produce these extra structures. For example, for a lattice, the diffraction pattern of sharp point spots is encoding something like the Poisson summation formula. The Fourier transform of a lattice is that delta functions at the point of a lattice is supported at delta functions on the dual lattice. Is there some explanation for that? And then, as I said, the dynamical systems come in describing these structures. And finally, if you try to describe electronic properties of quasicrystals, which have something like an insulating properties, then models for that have used C-star algebras and C-star operator algebras. But in this talk, I am mainly concerned with the geometric models, although I'm going to say something about what you get in diffraction. So there are two sorts of models you might think that are discrete geometry representing the atoms. The first is tilings of space, each tiling representing a region associated to one atom, or Delaunay sets. And in this talk, I will consider only the Delaunay set models, but you can kind of go back and forth. So you can certainly convert to a tiling to it. If you have a tiling with a finite number of tiles, you can convert to a Delaunay set by putting some marks on the tiles, which will correspond to points, and marking different tiles with different sets of points. Then you can produce a Delaunay set from a tiling. And in going the other way, there are many recipes known. For example, taking the set of all closest points to each point gives you Voronoi cells of Voronoi regions. The questions I would be interested in here will correspond to point sets that are as close to crystallographic as possible, which means we want them to have some kind of nice symmetries at some level. And one aspect of that will be that we'll only allow a finite number of different Voronoi regions. Before going on, I'd like to say something about the issue of local rules. This is all I have to say about how they might form. If we have a discrete geometry structure, a Delaunay set, we can have some recipe that says we only allow a finite number of local configurations of the points. So that would be what would correspond to local rules. So crystals have this property. There's only, at each point of a crystal, in the ideal crystal, it extends the regions of the same all the way out to infinity, or there are a finite number of different such things. But in particular, locally in some balls, say radius 50 angstroms, there are only a finite number of allowed configurations up to isometry. So a weak form of this is that we allow structures that are built up only allowing a finite number of local pieces to put them together. And perfect local rules will be the very rare case where the local rules have the property that every structure you build out of them, every infinite structure, has to be the same in a certain strong sense. And the sameness is that they all look the same locally. So if you take a piece of one of them of an arbitrarily large size, then in any other one made by these same rules, you'll be able to find a copy of that piece. So if you only can look out to a finite distance, you could not tell these two structures apart, because every region of that diameter will be, you can find them in both. This is a weak motivation for this sort of thing. If you consider that the structures are being formed by some sort of energy minimization, with some sort of minimizing some sort of local energy around each atom that is determined only by stuff within a finite range, and if you believe that this thing has finitely many minima up to rotations, then the discrete geometric analog of that would be to put on a requirement that they satisfy local rules under isometries, that you only allow a finite number of local arrangements of the points to some diameter. In this case, diameter 2r, where r is the big radius of the Delaunay set, turns out to be sufficient. Also, for later use in describing things, my object will be to present some examples of the two mathematical constructions and these definitions. So a lattice is a discrete additive subgroup that spans r to the n. So that's a full rank lattice, rank n lattice. I'm going to allow an object called a quasi-lattice, which will still be a finitely generated additive subgroup that spans r to the n, but which might have more generators than the dimension of the space. So all in it. So we allow rank r where r is bigger than n. if R is bigger than n, then typically the set of points you get that way will actually be dense. So it'll be a finitely generated additive subgroup, but it need not be discrete. And then finally, in describing Delaunay sets, I want the notion of a patch. So a patch in a Delaunay set is the set of all points, a t-patch. A patch of radius t has this point marked as a center, and then it looks at all the points within radius t nearby. So that will be the local information about that Delaunay set within radius t of a point. Finally, this is a technical slide on the notion of diffraction. So this is a mathematical. There is now a nice model, rigorous mathematics for parallel beam diffraction developed by Berthoff, which involves the use of measures and tempered distributions. And for a Delaunay set, we will think of a Delaunay set as a tempered distribution with delta functions at each point. Then you can form a two-point correlation measure associated to that by some kind of limiting process over large regions. And if that thing is well defined, then its Fourier transform turns out to be a positive measure. And therefore, by the Lebesgue decomposition theorem, it can be decomposed into a pure point, absolutely continuous, and singular continuous pieces. And in this framework, the pure point piece ought to correspond to the spots in a diffraction photo. It's not exactly true, but that's the mathematical model we will use. And that's when I talk about diffraction, I'm going to use it will be in terms of this model. So there are two Delaunay type constructions that produce things that can exhibit pure point diffraction structure with extra symmetries, as is observed in the quasicrystal electron micrographs. And these are a cut and project construction, which was in fact invented as an aspect of harmonic analysis, pure harmonic analysis, prior to the discovery of quasicrystals by Yves Meyer in the early 70s, where he called these things model sets. And the second kind will be subjects that have some sort of self-similar symmetry on bigger and bigger scales. So this is the setup for cut and project sets. The thing we want to construct, the lattice, is this X. This quasicrystal object will be a point set X, a Delaunay set in n-dimensional space. What we do is we take a lattice in r-dimensional space where r is bigger than n, and we project it down. We project it down from r to the r to r to the n by some projection, and then in a different direction we have an orthogonal. We have a projection onto the orthogonal complement, and and the restriction is we do not project all points of the big lattice. We only project those points whose orthogonal complement falls onto a compact set called the window. So I should show you a one-dimensional example to make this concrete, the Fibonacci quasicrystal. So the Fibonacci quasicrystal will be a set of non-periodic set of points on that line there, and they are obtained from a two-dimensional lattice by orthogonally projecting onto the line. So this is the project direction perpendicular to the line, and the cut direction is parallel to the line. So this is the orthogonal projection, W perp, and this is the window here. The window is this unit interval here. So what we do is we project all lattice points in the two-dimensional lattice that fall within that strip, and we project them orthogonally onto the line. And it happens the line has slope 1 plus the square root of 5 over 2, and so you get a nice pattern of two kinds of tiles, a small one and a big one. So locally, the distances between consecutive points are only of two sizes. And that is what you get with a cut and project set. And the good news is for cut and project sets, and I should say this construction has been generalized. So it turns out that in the perpendicular direction, you didn't have to use r to the n, But you could have stuck in any locally compact abelian group. So you could stick in a p-adic group, for example, and they're very nice constructions of quasicrystal-like Delaunay sets that have some kind of internal p-adic structure built into them. For example, the chair tiling exhibits this. But one can rigorously prove they're pure point diffractive. The diffraction measure you get associated to these things is pure point, and it's supported on a quasi-lattice. And in very rare cases, there are a few of these objects that have good local rules, but they come from the next kind of construction that I will show you, which is...
So what you have, you take the inverse image of W and then you project it?
Yes.
Okay, so.
Yes. So the second kind of structure is most easily visualized with tilings. So the chair is this object with 3 cells, this L-shaped triomino, and if you blow it up by a factor of 2, you can fill it with 4 copies of itself. So now you can keep inflating by powers of 2, and you cover bigger and bigger areas of space. And there, in the limit, you can cover space with these copies of this self-similar chair tiling. And it's that factor of 2 that leads to a 2-adic structure associated to this. And the good news for these things is, in a very strong sense, it's been proved that any such self-similar construction, modulo some technical hypotheses that turns out to have perfect local rules. So some local way of describing how the hierarchy is formed, and then that will make it fit together on every possible scale. And in the other direction, it is known for some of these objects that they're pure point diffractive, and for others of them they are not. And there are definitely open questions in that area as to when you get it, what you don't, what the rest of the spectrum looks like when you can get singular continuous spectrum, but can you get absolutely continuous spectrum? It's not known. Now, this Fibonacci example that I showed you actually occurs in both constructions at once. So I described it as extracted by a cut and project procedure, but there is one Fibonacci construction. So in this construction, if I shift the lattice, well, let me say, if I shift the unit mask sideways, I will move the points about, and I will get different Fibonacci quasicrystals, and they are the same in the sense that they all have the same set of local regions, so they cannot be told apart locally. So there's an inflation rule for generating the spacings by taking a long tile and a short tile, and when the short tile is inflated, it becomes a long tile. When the long tile is inflated, it becomes a copy of a short plus a long. And so if you inflate by this substitution rule, A goes to AB and B goes to B, you can produce an infinite string of symbols, and those will represent the spacings of the 2 features on the Fibonacci quasicrystal. A famous 2-dimensional example comes from Penrose tiles. Now, I will represent here the Penrose tiling represented with the kite and the dart. Again, there's an inflation by 1 plus the square root of 5 over 2, where 3 plus the square root of 5 over 2, where an inflation of... There is an inflation rule to describe these things. In the version I'm showing you here, it's actually, the inflation rule is not visible, I believe, using kites and darts. You have to use one of the other configurations. But I'm going to put points at the corners to get the Delaunay set. The points are Kellered 2 Kellers, and the rule for forming the tilings is that when you put the tiles together, the red points must match with the red, and the greens must match with the green. And that actually gives you perfect local rules for Penrose tilings. The set of infinite tilings you can create that way. All will look locally the same everywhere. Now, let me say something about pure point diffraction. In these examples, the Delaunay set constructed this way always has its points contained in a quasi-lattice of rank R. So it doesn't span the quasi-lattice because it's a Delaunay set. It's a discrete set, whereas the quasi-lattice is dense. But it will be some very thin subset of points in the quasi-lattice of rank R. And then the pure point diffraction spectrum associated to it will be supported in a dual quasi-lattice of equal rank. And if it were discrete, you would recover the crystal situation where the rank is equal to n. But if the rank is bigger than n, in the cut and project construction, the spectrum is necessarily dense. So why don't you see that in the electron micrographs? The reason is the electron micrographs only see the brightest points in the diffraction spectrum. So if you turn up the intensity of the X-rays with a crystal, you will simply see the same points darker. But if you turn it up on a quasicrystal, you will see the same points darker plus some new points, which will represent more of the spectrum that's actually a dense set, but you cannot see it all.
People see that in experiments?
Yes, they have tried this and they have seen it in experiments. I mean, they can't turn up the intensity indefinitely, but they've... Okay, so now I'm going to go to the discrete geometry side and describe something about Delaunay set models. So here is a hierarchy of ideal crystals will be the most, if you like, the most symmetric objects. And in this hierarchy, the next object you see are cut and project sets. And then something slightly more general called Meyer sets, which are very closely related to these two. And then I will define a notion of Delaunay set of finite type, which corresponds to objects having finite local complexity, and then finitely generated Delaunay sets. So the definitions are a Delaunay set will be finitely generated if the inner point differences between the points span a quasi-lattice. Now, normally the inner point distances for a general Delaunay set would span an infinite dimensionally, give you an infinitely generated discrete group, but here the insistence is they are sitting inside some finitely generated object. The rank of that object would correspond to that means they sit inside a quasi-lattice of some rank. A finite type Delaunay set is one whose inner point distances form a discrete set. Let me say closed so there are no finite limit points. And a Delaunay set will be called a Meyer set if its inner point distances themselves form a Delaunay set. So some of these inclusions here are theorems now. They aren't obvious from the definitions. So, for example, one can show that for Delaunay sets of finite type with the restriction that the inner point distances... Now, the inner point distances are very relevant to diffraction because the diffraction is some kind of Fourier transform of the two-point correlation. So it's a Fourier transform of the inner point distances counted with a weight. So a set X is a Delaunay set of finite type. Then, if and only if, it has only finitely many types of patches of radius 2r, where 2r is twice the Delaunay constant. This is finitely many different patches of up to translation. And that turns out to be equivalent to having finitely many types of patches of any radius, with the number of different patches will grow with the radius typically. For a crystal, it would stay constant from some point on, but for these sets, it will continue to grow as the radius gets bigger. Another way to say it is that the Voronoi cells associated to the points of the Delaunay set are of only finitely many kinds. This is the Voronoi cell with the center marked. So that means it has finite local complexity. Well, what do you get out of that? What you get is that since it has only finitely many local regions, since it has only finitely many kinds of local patches, that you can prove from that the thing is embedded in a quasi-lattice. And since it's embedded in a quasi-lattice, it's finitely generated, so the points in it will span a finite dimensional vector space. Take that r-dimensional space, and embed it in the integer lattice, and just take orthogonal, just take projection down onto the original variables, and then if you take any complementary subspace, you can project an orthogonal complement, and then there will be some image of the lifted points. That is to say, we take x and we lift them up by their coordinates as a linear combination of these, of some spanning set. So you pick in this construction, you pick a basis for the quasi-lattice and use that to get coordinates. And then one can ask the question, what happens over here? So if you have a Meyer set, for example, or a cut and project set, the region that you will project down to in this direction will be compact. But for more general Delaunay sets of finite type, it will be more complicated. So this kind of viewpoint of looking at these objects is a bit like Gromov's way of looking at high-dimensional spaces. So you can say that in some sense the structure of the Delaunay set of finite type you get this way can be described in terms of this address map by asking what is going on in the internal space, the extra dimensions that you've glued on to describe it. And one characterization is that it's a finite type if and only if this map is a Lipschitz type map. So the projection in the internal direction will spread out over the whole space, but the distance measured there will be within a constant of the distance in the original space. And there's a very nice description of a Meyer set in this term, which is the address map is almost linear. There is some linear map from R to the n into R to the r, which when projected down, the distance between in the complementary direction, the projected map will be within a constant distance of a linear map. And this theorem is due originally to Meyer and in an elegant form by Bob Moody. In terms of this taxonomy, one can also describe self-similarity structures. So if you have a Delaunay set with the property that you inflate it by some constant, some real constant bigger than 1, with the property that the inflated points form a subset of the original set, then it places very strong restrictions on the inflation constant. So if it is finitely generated, then tau must be an algebraic integer. And if it's a finite type, then tau must be an algebraic integer, all of whose conjugates are smaller in real algebraic integer, all of whose conjugates are smaller than or equal in absolute value to the original number. And then finally, if it is a Meyer set, it must be an algebraic integer with the property that all of its conjugates lie in the closure of the unit disk. And all three of these implications are actually if and only if you can construct sets that for each of the allowed constants, you can construct sets that achieve it. So now let me go on to the dynamical systems viewpoint. The dynamical systems turn out to be useful in two different ways. They are useful in describing the global symmetries of the object, which will now be statistical symmetries. And statistical symmetries are what you actually capture in a diffraction pattern, in a diffraction photo. So they allow you to describe objects with many, with interesting symmetries, and also they can be used to formalize diffraction in a different manner that occurs before. So the dynamical system viewpoint is the following. In a crystal, the object looks the same every place. But here what will happen is we have weakened the notion of being matching over the entire space to being that you have some kind of approximate matching over large finite regions of arbitrary size. So we will say two Delaunay sets are the same or locally isomorphic if they cannot be torn apart locally in any finite piece, which means every patch of one occurs in the other and vice versa. Now we can associate to a Delaunay set, we can associate a dynamical system as follows. We first translate the set around, and then we look at the patches near the origin, and we form the closure in a certain topology. And topology is to say that two sets are close if they're within epsilon of each other in a very large disk around the origin, say of radius 1 over epsilon. So that will define in fact, one can put a metric topology on this space. And it turns out that if you take a Delaunay set of finite type, or finite local complexity, and you apply this procedure, then the closure will give you a compact topological space. And because we are moving sets around by translations, this set will be closed under the action of translations. So the dynamics will be the R to the n action by translation. So if you iterate a map, you have a single action by z, and if you have a continuous flow, then you have an R action. But here we have an R to the n action. Well, we are if you take the closure, if you applied this to a crystal, for example, and you took its closure, all the translates of a crystal, the only freedom they would have would be to move around in the unit cell of the crystal. So every object that would be in the closure would be a copy of that crystal translated around in the unit cell. So the dynamical system is very simple then. The object is a point plus a unit cell, and then the R to the n action will be modding out by the lattice. But now for these exotic objects, things will be more complicated. In topological dynamics, but we want things that correspond to crystal. Well, what will correspond to crystal will be something that when you move it around, you don't get anything new. So the notion of that in topological dynamics is of minimality. If you take an orbit, we move one of these objects around by translations, then that will be dense in the whole thing. And minimal is that every orbit is dense. In this case, we have taken the closure of a single orbit. So that orbit was dense, but there might be new orbits inside that are not dense because you might get new objects. But in this sense, the set cannot be taken apart. And the geometric interpretation of that is called repetitivity. A Delaunay set is repetitive if any patch that appears in it appears locally in any finite region. The set of centers of each of the patches, copies of this patch itself, will form a Delaunay set, probably with a much bigger value of R. So that you can't find any large region of the object that emits a copy of this patch. So, for example, the Penrose tiling is linearly repetitive. It's been proved that any copy of a patch of any patch of size 14t contains a copy of every patch of size t inside it somewhere. Well, I'm not going to say too much more about dynamical systems. I'm going to show the connection with diffraction, but the basic usefulness of this is that, and I should say this viewpoint was strongly put forth by Charles Radin, Boris Salomyak. The dynamical system encodes all the statistical symmetries, this compact object with the R to the n action. So, for example, the idea of being a ground state in a statistical mechanics system will correspond to this minimality property in some loose sense. The second thing I will mention is that the pure point part, the diffraction spectrum, can be recognized in terms of the eigenfunctions of the R to the n action on this dynamical system. And then, finally, extra symmetries can be reflected as extra symmetries of the closure of this orbit. Well, maybe I should give you two examples. So one of the very nice features of this viewpoint is that, in a certain sense, the dynamical spectrum associated with the dynamical system spots the pure point diffraction spectrum. This was in a topological version. It's Radin and Wolf, and Salomyak, Moody, and other people have recently got a stronger form. So let me at least give you the definition. You take in topological dynamics, you take the compact object X, then a continuous eigenfunction. So X is a space of Delaunay sets, or a space of tilings. A continuous eigenfunction is a continuous map of this topological space into complexes, such that if you move things around by translation, so we move so P is a tiling, or a Delaunay set, we move it around by translation. The action is unitary, so it'll be e to the 2 pi I but we are doing the whole R to the n action. So we are doing a joint action of all these operators at once. So the action will be e to the 2 pi I t dot x, the inner product of t and x. And then that value x and R to the n, which is determined by this will be called the joint eigenvalue. Now, the eigenvalue is actually the unitary thing, but the x to the R to the n completely describes it. So we call that the eigenvalue. And that point x will correspond to a spot in the diffraction pattern if you have a continuous eigenfunction with that value of x. In the metrical dynamic version, we need an invariant measure on the space that is invariant under the R to the n action. And then we have a notion of a measurable eigenfunction, which is an element of L2, which obeys the same equation. Translations multiply by a unitary constant, depending on the translation. So the point is, it's got to do this for the full set of t and R to the n. Then what they have shown in the most recent version. In this version, the eigenfunction doesn't tell you anything about the intensity of the spot. But the theorems you get are in a closure of these systems. Every Delaunay set in such a system will have a pure point diffraction spectrum where the pure point stuff is supported at all of these points, but the intensity of the spots might depend on which item you have in the set, in the closure of the set, which particular Delaunay set you have. To finish in this vein, these studies also led to new objects. So Charles Radin and John Conway have a construction of a inflation tiling that allows all rotation, so that unlike the case of a crystallographic object, the associated dynamical system has a continuous symmetry with the full two-dimensional orthogonal group, even though the object is built with local rules, with a finite number of copies. Now, because of the time, I'm not going to be able to give you the complete list of comparing what happens, where is the boundary between crystals and aperiodic objects that are not crystalline. I will give you a single example. So the single example is that a property that an ideal crystal has, as I defined it, is that the number of patches of a given radius is bounded up to translation. There are only a finite number of patches of a given size, and that actually is constant for a large size, whether you would do it by translations or by isometries. So this gives a local characterization of crystals. This is something about what the thing looks like locally in some radius is sufficient. There's actually a stronger form of that. Here is what happens if you relax it. If we relax it to say it has a finite number of patches of each radius, but the patch grows like constant times t to the n, where n is the dimension of the space, then there do exist completely aperiodic Delaunay sets which have such a patch growth function. It is a conjecture that if you insist on complete aperiodicity, you cannot have a growth rate slower than t to the n. That has been proved in dimensions 1 and 2 only. It's an open problem that, to give you an example, if I took a crystal and I stuck in a single defect at one point, then that would make the number of patches grow like t to the n. If I took a crystalline pattern and I just added one point, because that point would be a black spot. So if you look at a patch of radius t, you can move the black spot around anywhere in the patch, and that gives you a huge number of patches that grows like t to the n. That's why we believe t to the n is the minimal growth rate you can get if you allow aperiodicity. Well, there are a number of other characterizations, but I believe I'm running out of time, so I will skip them and make two concluding remarks. So what has quasicrystal, the study of what mathematical results have come out from trying to understand the nature of quasicrystals? First of all, we now have a much sharper understanding about local properties that determine the boundary between periodic and aperiodic structures. And this would not have occurred if the existence of very nice aperiodic structures had not been exhibited by the existence of quasicrystals. Second of all, the viewpoint that connects dynamical systems and harmonic analysis turns out to be very useful in discrete geometry problems and in the study of diffraction. And I will say more about that in the sphere packing talk tomorrow. Finally, it led to the construction of, or the understanding of, a taxonomy of aperiodic sets, including some perfect ones, which could model this aluminum, copper, iron quasicrystal. And then finally, it has led to the study of how discrete objects can carry new kinds of symmetries that are not visible on the for example, on the Penrose tiling, a single Penrose tiling does not exhibit the five-fold symmetry. It statistically exhibits the five-fold symmetry over large regions, but it doesn't have a perfect five-fold symmetry built in. It's at a local level. Also, just even though this is discrete geometry and not dynamical systems, I would like to say, as this is now off the subject slightly, it has to do with the Hilbert problems. So the Hilbert problem list has 23 problems. And of those 23 problems, there are a bunch of problems that are research programs. For example, problem 5 is to axiomatize physics, which cannot fairly be said to have been carried out at this point. And then there were a bunch of very specific problems. And of these specific problems, every one has been solved but 3. And these 3 are the following. Number 8, the Riemann hypothesis. The second part of problem 16, which is the existence of a finite number of limit cycles for polynomial vector fields in the plane. And the last remaining problem in problem 18. I should have, of course, Kepler's conjecture has apparently been solved by Hales, although the refereeing process has now dragged on for 5 years and is not complete. But the second part of the remaining part is, what is the densest packing of regular tetrahedra in R3? No one has a clue that I know of, has a clue on this problem. So the point I want to mention is, where does the difficulty in these problems come from? Well, you would get a lot of, this is a debatable thing, but I would like to point out that apparently each one of these problems is associated to a dynamical system. In the case of the Riemann hypothesis, it's an unknown dynamical system. But if it did exist, then a lot can be said about what it's got to look like. The limit cycle problem for polynomial vector fields itself is a dynamical system all the way. Anyway, and finally, if you're trying to understand the densest packing of regular tetrahedra, then you can associate to any such packing a Delaunay set by marking one vertex in the centroid. We want to mark enough so we know that how the tetrahedra are rotated, because in this problem the difficulties come from the fact that the tetrahedra is going to be rotated and they presumably don't have the same orientation, and maybe the densest packing will be aperiodic. But attaching a Delaunay set that way, you can easily concoct a dynamical system, a compact set with an R3 action, and it may be that that particular dynamical system will give interesting insights into this problem. Thank you.
In the cut and project method, is there any understanding of what might correspond to the extra dimensions physically?
Well, I will give you my answer, which the physicist. It isn't the cut and project per se. It's the fact that you get a set of finite type that way. The existence of the mechanism is, we believe that crystals and quasicrystals are locally minimizing some energy functional. Now, electromagnetic is long range, but let's assume somehow it's being approximated by short range and some finite radius. Then if you believe finitely many minima, then you only allow finitely many different local minima up to rotation. One can prove that if you have finitely many local minima up to rotation, you can concoct a bigger set of local rules that will fix it up to translation as well. Once you have finitely many local rules up to translation, then you have a Delaunay set of finite type, and the quasi-lattice is built into that. But now the dimension of the extra dimensions is coming from how many minima there are. It's coming from something having to do with the underlying functional that's being minimized and how many minima how many local minimum it has. That is a recipe by which you could say that why could it be that the atoms, after all, are getting somehow put into position because they're trying to minimize their energy with respect to whatever is going on around them. Now, this is a cheat because the electromagnetic force, unfortunately, does not satisfy these hypotheses, so they don't really have a clue. But this is a story where it might be coming from.